Should there be a button up there? Yep. Thank you for attending today's talk. So initially I planned on talking about subsampling based model selection, but there has been a change of plan, and I'll talk about subsampling based community detection, and then I'll do some review on model selection problem. So any data that can be represented using a graph is a network data. It usually involves different actors who interact with each other, and we usually represent those actors using nodes in the graph and the interactions using edges. So for example, a common example is social network. So if we look at Facebook network, they're like, we can think of the users as nodes, and if two users are friends on Facebook, then they are connected by an edge. Similarly, we can have biological network where we look at, like, say, epidemiology, how COVID or any other pandemic spreads, or we can look at gene interactions between genes or proteins. Similarly, we can have other kinds of networks as well. So this is an example of a US air transportation network. Here, each node represents an airport within the US, and two airports or two nodes are connected by an edge in this network if there's a direct flight between the two airports. Similarly, here's another example. This is a karate club network. So each node represents a member of a karate club, and they are connected by an edge if they interacted outside of the karate club. So this is an interesting example for community detection, because at some point the karate club, there are two instructors in the karate club, and at some point the karate club split into two different clubs for each instructor. And it was observed that almost half the students went to instructor 1 and the other half went to instructor 2. And it was observed that the students that went to the same instructor interacted more outside the class, outside the club, and the students who went to different instructors, they interacted less. So there are different ways of defining communities in a network. So the block model idea of community is that if two nodes belong to same community, they interact more, or there are more edges between them, or there's a higher probability of an edge between them. And if two nodes are from different communities, there's a lower probability of having an edge between them. So when we have a network with some underlying community structure, an inference problem of interest is to detect those communities. So for each node, we want to assign a community label, and we want to detect those communities. So there are many existing methods that are very well, like spectral clustering, which does an eigen decomposition of the entire adjacency matrix, and then based on that it does some kind of clustering. There are some likelihood-based methods which maximize the likelihood of a particular community structure. And similarly, there are some convex optimization-based methods as well. Now, all these methods are very accurate, but they do not do well for large networks in terms of computation time. So nowadays, we have large networks appearing almost everywhere. Social networks are huge, and with those computer-generated data, the networks have like millions of nodes and billions of interactions between them. So, and in those large networks, all those methods are very slow, and they require a lot of memory to work. So our method is to develop an algorithm that is parallelizable, so that we can perform computations on different computers and store the network in different parts. That way we can save both time and memory. And the method should be flexible or adaptable to a wide range of community detection problem, and there should be some theoretical guarantee that it works. So this is the broad notation I'll follow. N is the number of nodes, K is the number of communities. For now, we'll assume that it's known. And script A is the community detection algorithm of choice. It could be anything. So our algorithm is called SONNET, or subsampling on network. So it has 4 major steps: division, detection, stitching, and repetition. So in the division step, we start with the entire network S, which has, say, n nodes, and then we randomly select O nodes at random and fix an overlap part. So we keep that part fixed, and we split the remaining n minus O nodes into S equal parts and call those the non-overlapping parts. So we have one overlapping part with O nodes and S many non-overlapping parts, each with M nodes. Then in the detection step, we form the subgraphs So we as we stitch we just attach the first non-overlapping part with the overlapping part, the second non-overlapping part with the overlapping part, and so on. So on all these subgraphs, the overlapping part remains the same, and we just have different non-overlapping part, and we apply our algorithm, any algorithm and any suitable algorithm, and then we get the community levels. So here we assume that there are only 2 communities, so we get either 1 or 2 as the community levels. So this is the detection step. So now we have the stitching step. So from this output, you can see that we have different sets of levels for the same nodes that are in the overlapping part. And for the non-overlapping part, we have different sets of levels. Now, the problem with these levels is that these levels are good up to their permutation. So if we flip 1 with 2, we still have the same set of levels. So for 2 communities, there are like 2 possible permutations, but for k communities, there will be k factorial possible permutations. So we need to match all these results. We have to stitch those back. So here comes the stitching step. So what we do is that we look at the first output from the first subgraph and the second subgraph, and we match the overlapping part because these levels correspond to the same set of nodes. And we see that in this case, the best permutation is just flipping the levels. So we flip 1 by 2 and 2 by 1. And in that case, we have a perfect match and have an error at 0. And we apply the same flipping rule or the permutation rule on the non-overlapping part as well. So we change the levels. Similarly, with the third one, we can see that the best permutation is just keeping the levels same, 1 as 1 and 2 as 2. But in this case, we do not have a perfect match. So this is the best permutation, which has an error rate of 1. The other permutation has higher error rate. So we apply the same permutation, or we just keep the same levels. Now, for large k, we have to scan over k factorial permutations, which makes it very slow. In those cases, there are some greedy algorithms that work well, and that reduces the computation time to k square from k factorial. And now, after the stitching step, these yellow part, the blue part, the non-overlapping parts are at par with each other because we match those using the overlapping part. But for the overlapping part, we have s different sets of levels. Here it's 3. So we take a vote over all those nodes. So for example, for the first nodes, we have 1 here, 1 here, 1 here. So we have 1, 1, 1, 2. So the vote will be 1. And we attach the non-overlapping, the output from the non-overlapping part as well. Now, in this process, we assign too much importance to the overlapping part because we are performing s many community detection on the nodes inside the overlapping part. But for the non-overlapping part, we are performing only 1 community detection. So the accuracy rate is very high inside the overlapping part, but not for the non-overlapping part. So to improve that, we have an additional step called repetition, where we repartition the non-overlapping part again and again, and then we just stitch using the same mechanism with the main output that we got. And we repeat this r times depending on our computation resources. So as we increase r, the accuracy increases, also computation time increases. So depending on our computation resource, we can decide on r. So here's the theory. So this theory is for stochastic block model. And here actually, this is the general theory. So we have for the theory, for the theoretical bound or the accuracy, we have to make some assumptions. So we assume that the community detection algorithm A is reasonably accurate on each subgraph. So this computes the error rate when I apply A on the qth subgraph. And we assume that this error rate is bounded by epsilon for each value of q. And the second assumption is that our choice of parameters O and S should satisfy this condition. So where pi mean is the proportion of the smallest network, the smallest community in the network. So O and S, and M is just M n minus O divided by S. O and S should be chosen such that this condition is satisfied. Now, if we have suppose we start with a bad community detection algorithm A, then this epsilon will be very high. And in that case, our choice of parameters will be very restricted. So if we start with a good algorithm A, then we'll have more choice of parameters. And under those 2 assumptions, we can show that the entire error rate can be bounded by this quantity, where we have the epsilon is the error rate on each of the subgraph. S is the number of subgraphs, O plus M is the size of each subgraph, and M is the size of the entire network. So this is like proportion of nodes used, proportion of the total number of nodes used in the process to total number of nodes in the network times epsilon. So ideally, we'd like it to be as close to 1 as possible. So this also gives us another idea on how to choose the parameters. And this is a probability statement because all these quantities are random. So I have omitted the probability term here. So now we can apply this on different problems. So I'll just present the stochastic block model or SBM case. So in SBM, the nodes are partitioned into k blocks or communities, and let Gi be the community membership of the ith node. Then we assume that the ijth entry of the adjacency matrix Aij follows Bernoulli B Gi Gj, where B is a k by k community probability matrix, and these are independent. So if I belongs to community 3 and J belongs to community 5, then it will just be 3, 5. So we have a k by k community probability matrix. And spectral clustering works very well on SBM. So spectral clustering just computes a leading k eigen vectors corresponding to the largest k absolute eigenvalues, and then arrange that in n by k matrix, and then apply k-means clustering. And this works very well on SBM. So we use this as the algorithm script A here. And we assume that the B matrix of this is of this form. B is alpha n times B naught, where alpha n is greater than log n over n. So we cannot have too sparse a network. So if alpha n is very small, then the network will be very sparse. So we cannot have too sparse a network. And under these assumptions, we can show that this is the error rate, which is it can be bounded by this quantity, which has 1 over n alpha n and the denominator. And also this bound gives us some idea on how to select the parameters S and O. So I have some simulation results here. I have an SBM with 10,000 nodes, 5 communities, and I have assumed that if 2 nodes belong to the same community, they have a probability of 20% of having an edge between them, and if 2 nodes are from different communities, they have a 5% probability of edge. So if I apply spectral clustering on the entire network, I get a perfect error rate, 0, and the average computation time is 18,000 seconds, almost 18,000 seconds or 5 hours. And Sonnet with spectral clustering, and if we use Sonnet with spectral clustering, we can get an error rate very close to 0, which is 0.3% in just 21 seconds. And there are some other cases where we can see that the error rate is slightly high, but the computation time is faster. And Gale is another divide and conquer method in the literature. So if we compare with Gale, we can see that Gale can also achieve very small error rate in fast computation time. It can get 3% error rate in 26 seconds. So, but ours still does slightly better here than Gale. So this is the model selection. This is the community detection part. So now the main problem with this community detection problem is that when we have a real network, we don't know the value of k. So we first need to choose k. So that leads us to the model selection problem. So we do not know k. And k is valid only for block model. So when we have some stochastic block model or degree corrected block model, we have the number of communities k, and we have to predict that. But there are other kinds of models like random dot product graph model, graphon. There we have to estimate their models as well. So there are 2 network cross validation method for model selection in the literature. I'll just do a quick review of those. So the first one is network cross validation. I'll call this NCV. And this is very specific to determining the number of communities in network data. And the second one is more recent work, network cross validation by edge sampling. And this is applicable to a wider class of problems. So the idea for node cross validation is that they just split the adjacency matrix, the entire adjacency matrix into V by V equal size blocks like this. And V is the number of cross validation folds. So for each fold, and for here we have a candidate value of k, we have to select one value from there. So we estimate the model parameters using the adjacency matrix except the Vth fold or the Vth submatrix, and then we compute the predictive loss on the Vth submatrix. So we can use likelihood based loss function or the negative log likelihood as a loss function. Another common choice is just squared error loss. And then we sum of those loss function over all the folds, and we just select the value of k from the candidate set that has the lowest loss value, that has the lowest loss function. And there's another idea, it's cross validation, where again we have v many folds, and this is slightly this has similar structure to that structure as NCV, but it uses a different method. So we choose a subset of node pairs. So instead of here we are looking at a random subset of node pairs omega, where we're selecting each pair independently with probability p, and the authors have suggested a probability around 90%. And for each candidate value of k, we apply some kind of matrix completion method on the submatrix A omega. So A omega is the submatrix from A which has the nodes in omega. And we apply the rank constant k tilde to obtain the n by n matrix A hat k. So they are performing matrix completion to get back the entire matrix from the smaller matrix. And then they are estimating the model parameters or performing community detection on A hat k tilde. And then they're computing the predictive loss on the remaining part, the omega complement, the part that wasn't used in matrix completion. And then summing over all the folds, we are performing a discrete minimization. So now both of these methods, the ECV method works very well. NCV is very particular and it doesn't work well for sparse networks. ECV works very well, but the problem with both the methods is that they are very slow, because here we are performing community detection, but but that time is multiplied by the size of this candidate set k. So this gets very slow. So in both the cases, they are performing community detection on a large subset of the entire adjacency matrix. So their methods are still slow. So we can use our sonnet kind of subsampling structure to perform model selection. So in sonnet, we are working with smaller subgraphs, so we can save computation time there, and we can use the same split as sonnet for each candidate value k tilde, and then we can just compute the predictive loss on node pairs that are between the non-overlapping parts. So when we are performing sonnet, we didn't use the node pairs between the non-overlapping parts. So we can use that as the cross validation set. And there's a common proof technique that both the papers used and I'm also using. So when the candidate value is smaller than the true value of k, we can show that the predictive loss is much larger than the oracle loss. Oracle loss is we just assume that we know the expected adjacency matrix and we compute the oracle loss based on that. So we can show that they showed that when k tilde is less than k true, the predictive loss is much larger than the oracle loss, and when k tilde is equal to k true, the predictive loss is centered close to the oracle loss. So we'll do at least as good as using the oracle loss. And this guarantees that probability k tilde less than k goes to 0 under some mild conditions. So yeah, we will also show the same thing. That's it.
Show that your estimated k hat will be smaller than k. So do you need to add some penalty term in order to prove the other side? You want to show your selected k should be smaller equal than oracle.
Yes. So for application, yes, we use some kind of penalty term with the loss function, but for theory, it's very difficult to show the other side. So for theory, we just so when k tilde is less than the true k, we using pigeonhole principle, we can show that there are two true communities that get merged into one predicted community, and that increases the loss function by a lot. But when k tilde is greater than k, the intuition is that there should be one true community. There should be at least one true community that gets artificially split into two predicted communities. So that should increase the loss function, but there's still no good method of showing that yet. But yeah, in practice, for simulations or real data examples, we use some kind of penalty term with the loss function to avoid overfitting. Yes.
For this one, In like your simulations, when you know the K in advance,
Mhm.
are there any diagnostics that came out of it that you know you could maybe plot and then would show you, hey, this is the good value for K? Is there some kind of like elbow plot or something where you plot the loss against K like that comes up?
Yeah, so usually what happens is that if you plot the loss function against different values of K, usually the loss function is low near the true value of K, and it increases on both the sides, but not with the same rate. And there's a tendency that it will be lower on the larger K side when we have overfitting. So so sometimes we need to make corrections for that. But yeah, usually we just try to find where it is the smallest.
I probably missed some things. So the Oracle loss is not necessarily 0, and that's because you have an adjacency matrix, and then from that, there's some map to the number of communities and who's in the communities.
Yes.
Okay, thank you for clarifying that. So my question then is, just when you do your simulations, this is, I guess, applicable to many things that people do with simulations. What kind of assurance do you have that the map that you're using to go from the adjacency matrices to the communities, that's representative of what goes on in real world communities? Is there literature on that?
So by real world communities, do you mean that?
The kind of things that are present in the applications you have, like in cybersecurity and these large networks.
Yeah, so yeah, in the simulation, I know the true value of K, and I can compare against that if I have got it right. But in real data, we don't know. But
well, not just K, but there could be many ways that adjacency matrices map to the number of communities, but then also, yeah, the
yes.
connectedness.
Like for example, in that karate club example, when you did K equals 2 for that one, was that actually where the lowest loss was?
Yes. Yeah. Yeah, the remote is not. Mehtat, could you please see if it's working? Yeah, let me show you one. I have one slide here. Yeah, it's working now. Thanks. So we assume that AIJs are independent Bernoulli B GIGJ, where B is a K by K community matrix. So this is how the adjacency matrix is connected with the community structure. And for Oracle loss, to compute the Oracle loss, we assume that we know this B matrix. But in real data, or when I actually performing the model selection, we just estimate this B from the Sonnet splits. And for real data, yes, yes, for some small scale real data, it has worked well so far.
But yeah, I get it. If you walk away or step away from this assumption, do something more complicated, it becomes a much bigger problem.
Yes. Yeah. Another question?
We don't have any more questions. Let's thank Sayan again.
Thank you.
Yeah, so lunch will be there in about 10 minutes in the common area in 212.
Yes, if don't mind.
Before you end the thing, it's good to tell them